Oh, thank you. I appreciate that. Thank you, guys. All right.
Oh, I have it.
You know, I did you have my packet?
I don't know.
Do you need one?
No, I had her packet on actually. I had hers and mine. Oh, what am I have two packets in my phone?
Wow.
All right. So today we are going to be doing 4-3 notes, which are nth roots. So in math, when you guys see an n, nth root, do you guys know what n means in math, like when we use it in this context? Yeah, it can be anything, yeah. So it's any number. So like it could be a second root, a third root. We use nth because it kind of represents a value in the future that we don't know yet. Yes?
What's the difference of n and x?
Good question. So nth is a set term. X is a variable rate, meaning variable means in real life and in math, a variable rate changes based on, other factors. So for example, we have an equation like 4x plus 3. X changes based on the point that we're looking at. Nth is a set amount. It's just an amount that is in the future. So it's kind of like a way of saying, like if we say 4, 5, 6, 7, 8, and then we say to the nth, we say that set keeps going on and on forever. So basically, it's just like a way of saying that without actually writing it all. So, yeah. Any other questions before we get started? Okay. So, blank page. All right. So let's just go over some simple radical vocabulary before we get started. So the index, okay, it's this little symbol here between the radical and like the little V shape in the radical. This tells you what radical we're taking, okay? So if it's squared, if it's third, if it's fourth. Now you guys are used to working with square roots. So square roots look like this. Square roots technically have a little 2 here, but we don't write them. So you know how we have an implied exponent of like 1 on a variable and an implied coefficient of 1? So radicals have an implied index of 2. So if it's anything other than 2, I'm going to give you a number there. So it'll be 3, 4, 5. But if it's nothing written, you're going to assume it's a 2. The radicand is what we call what's inside the radical. So when I refer to the radicand, I'm referring to anything inside of the radical. And then you get an answer, okay? And you can always undo that by putting it to the inverse power of the index, okay? It's going to basically give you back what you had. So you know how sometimes in math we have the square root of something and we square it to get rid of the square root? It's the same idea. So we're going to talk about the number of nth roots. So if your index is odd, so odd numbers like 3, 5, 7, so on, any real number, okay, it's always going to be one real solution. And we're going to look at 2 examples of that. So first one we're going to look at is the third root of x. Third root of x. Thank you for letting me know. So this will be, anybody know what the third root of, 8 is? So if I put it this way, somebody say 2?
I did.
Good. So the third root of something is what can you multiply together 3 times to get back to your original, okay? So 2 times 2 times 2 is 8. Anybody know what the third root of negative 1 is? Negative 1. Good, because I can multiply negative 1 by itself 3 times, and I end up with negative 1. Now if you have an even index, so a normal square root is an even index, what you guys are used to taking, a 4th root, a 6th root, and so on, that's always going to give you 2 roots. So you know how we do that plus or minus thing, where we put plus or minus in front of a square root? That stems from this idea, if you end up with 2 solutions. And that's because there's 2 situations where this can occur. Anybody know what the answer is to the square root of 4? 2. It's not just 2, but it's plus or minus 2, because not only is 2 squared 4, but also negative 2 squared is also 4. So there's 2 answers that will suffice. And then what is anybody know what the 4th root of 16 is? Very good, guys. So what can you multiply together 4 times to get to 16? That would be 2. Now, if you take the square root of a negative number, what happens? Do we get a real number as an answer? No, we get a what kind of number? We get 2 imaginary, actually. Okay. No real. 2 imaginary, no real. If you want to write no real, you don't have to, but I just like to mention that. So, anybody remember what the square root of negative 4 is? 2i, so plus or minus 2i, very good. And what is the fourth root of negative 16? Plus or minus 2i as well. So that is how we deal with interpreting the index, the sign of the index. So now we're going to talk about perfect cubes, perfect squares, and perfect fourths. So perfect squares are produced from numbers that you put to the second power and you obtain. So, for example, what would 1 to the second power be? 1. What would 2 to the second power be? 4. So these are your perfect squares. You guys see the gist of it? And then moving on to be 9, 16, 25, 36, 49, and so on. You guys get the gist of the perfect squares. Okay. So that's how you get perfect squares. You take a number and you put it to the second power. Okay? And what you obtain is a perfect square because you can take the square root of it. Bless you. So now we're going to talk about perfect cubes. So if perfect squares are numbers we put to the second power, perfect cubes are numbers that are put to the third power. So some typical ones you'll see is 1 to the third power, which is 1. 2 to the third power, which is 8. Anybody know what 3 to the third power is? 27. 4 to the third is 64. So that's how you get perfect cubes, and you can keep going. 5 to the third is 125, and then after that I don't have it memorized, so that's the general idea. And then if perfect cubes are putting it to the third, what do you think perfect fourths are? Putting to the fourth. And 1, you always start at 1, which is 1. What's 2 to the fourth?
16.
16. Anybody know what 3 to the fourth is?
No. I'm done. Oh my god.
Something 1. 81. Because
21.
3 to the fourth is the same thing as 2 to the 9 to the second.
Oh.
So.
Yeah.
And then 4 to the third, well, I don't know anymore after that off the top of my head. That's 16 times 4.
Wait, 4 to the third?
Oh, I meant to say 4 to the fourth, not third. 4 to the fourth would be 256. Just put it to the fourth power. Alright, so do you guys have a general idea of what this is right now, what we're doing? Okay. So, now we're going to go into simplifying radicals. So the first half of this lesson is going to be numerical simplification, and the second half is going to be where we throw variables in. It's not bad, it's just a different concept. So let's go ahead and simplify the basic ones here. So anybody know what the square root of 121 is? 11. Not only 11, but it's plus or minus 11, right? Because if there's no index, it's an implied 2, which is even. Now, this is the third root of 343. So, so everybody's going to have a varying degree of how comfortable they are with factoring off the top of their head. So something I always suggest to students is if you don't know what the factors are, take your number and divide it by numbers 2 through 9 until you get one that divides. Typically, you're going to find one within those numbers. When I do that, I get 7 and 49. This breaks up into. So you circle the 7 because it's prime, and we can break down the 49 into what? 7 and 7. Now, when you take a third root, you're looking for groups of 3 of that number, and that's what gets to leave the radical. When it's square root, it's groups of 2. So what is the third root of 343? Not plus or minus 7, but just 7. So do you guys see when you use plus or minus and when you don't?
Yeah,
It's an odd index. 3 is odd, so that's why we don't put the plus or minus. This is an implied 2, which is even. All right, next one. So we're doing the fourth root of 2,401. So, do I know off the top of my head what this is? No. But I think about it for a second, and I think, okay, well, let me try 7, because I know it's not going to be an even number. And 7 works, and that breaks up into 7 and 343. I circle the 7 because it's prime, and I break up 343, which I did earlier, which I know breaks up into 7 and 49. I circle the 7, and I break up the 49 into 7 and 7 as well. Now, if we're looking for pairs of 3 for a third root, what do you think we're going to be looking for over here? A pair of 4. Or a set of 4. I shouldn't say pair because pair means 2, but we're looking for 4 of them. And is this one going to be plus or minus or not?
Yes.
Yes, because it is even. So this is plus or minus 7. Now, the next one is actually a negative number. And you can't take the square root of a negative number, the even root, without getting an imaginary, but you can take an odd root of a negative, and you'll see why. So, what are some factors of regular 125? Anyone know? 5 and?
25.
5 and 25. I'm going to make the 5 negative and the 25 positive. I usually make the prime negative if I can. And we have to make it negative because one of those numbers is negative. The only way to get a negative is to multiply a negative and a positive, right? I'm going to circle my prime, and then I'm going to break this up. Now, remember, your goal is to get a pair of what in this case? 3. Am I going to get a pair of 3 if I make it 5 and 5? No, but what can I make it instead? Negative 5 and negative 5, which would still be sufficient and multiply back to 25. So, do I have a pair of the same number 3 times? Yep, so that gets to leave the radical as negative 5. No plus or minus because it is an odd index.
It's not imaginary?
No, it's only imaginary if it's an even index. It's okay to take odd index negative roots because odd numbers can come in negative pairs, but even numbers cannot. Okay, so let's go ahead and do E together. So for letter E, we're looking for a pair of 4, okay? So what can I break up this into? Any ideas?
8 and 500.
Oh, yeah, it works. Yeah, I think that works. So, yeah, you checked it in your calculator?
No.
Okay, we're just going to double check.
I just tried to divide it in my head. But
Good, that's a good job. Yeah, you're right. So this is 8 and 512.
How?
Because you look at the 40 and you look at the
Yep.
Or
Yeah, because 40, well, if you guys quickly do want to know, so 8 goes into 40 5 times, and 8 goes into 96 12 times, so it's 512. So what can I break up 8 into? 2 and 4. And then what can I break up the 4 into? 2 and 2. 512, what does that break up into? Yeah, I think it is 64 and 8. Yeah. 6 and 64.
we were at 8, that's 6. You said 6 and oh, 6. Never mind.
Okay. And then this breaks up into 2, 4, and then this breaks up into 2 and 2. And then 64 we know breaks up into 8 and 8, which breaks up into 2 and 4, and then 2 and 2. This gets very big. So there is a faster and easier way to do these sometimes, but I just want to show you the way that works always. So you circle all of these, and we have what we call our prime factorization. Okay, so go ahead and count up how many 2's we have. How many do we have here? 12. So if you multiplied all 12 of these 2's together that are your prime factorization, you'd end up back with your original number. That's what prime factorization means. So we're looking to group these in pairs of what? 4's. So go ahead and group them in pairs of 4's.
This reminds me of like that game 2048 or whatever.
Oh yeah, kind of, yeah. This particular number, because it is one of those factors.
Yeah. You don't know what 2048 is?
You like combine the bricks.
It's like a 20 like it's like an array and it has like blocks of 2, blocks of 4.
You have to swipe them and they multiply together. And you always get like 512 and then 1040, 24 and all that.
Whoa, man, I've never gotten that far.
So, anyways, so we group them into pairs of 4, and anything that gets paired up gets to leave the radical. So I have a pair of 2's that gets to leave, this pair's gone, and then anything that leaves gets to be multiplied together. So I have another pair that gets to leave right here, and then I have another pair that gets to leave. Do we have any leftovers? No. So our answer is, well, it's 2 times 2 times 2.
8.
8. So yeah, your answer here is 8. But not just 8, it's
Plus or minus.
plus or minus 8. Now you could have also done this by seeing that 8 times 8 4 times is this as well. So that also works, but I just wanted to show you the prime factor way too. So now we're going to do radical fractions. So these are actually really not hard at all. All you have to do is if the fraction simplifies, you can simplify it, but if not, you're just taking the square root of the numerator and the denominator. So this one is an even root, so it's going to be plus or minus. And then what is the square root of 4?
2.
Square root of 25?
5.
That's your answer. That's it. Alright, moving on. Now we're doing an odd root. So do we need to put a plus or minus here? No. So this whole thing is negative. So in my opinion, it's easier to view it as one of these numbers being negative. So I just bring my negative sign up to the numerator, which is totally fine. So what is the third root of negative 1? Negative 1. And what is the third root of 27? 3. So your answer is negative 1/3. Okay. Now moving on, we're going to be taking the fourth root. So do I need a plus or minus here? Yep. What is the fourth root of 81? 3. And what is the fourth root of 64? 2. So your answer here is plus or minus 3 halves, or 3/2. So far, so good? Makes sense? Okay. Now, the next part we're going to be looking at is a regular square root here. Anybody know what a factor of 117 is? Well, it's 9 and 13. Which one of these numbers is prime?
13.
13. 9 is not prime, right? 13 is my favorite number. So what does 9 break up into?
3 and 3.
3 and 3. So, we're looking for pairs of what in this case? 2, because it's a regular square root. So I have a pair of 3's that gets to leave, and what has to stay behind?
13.
13. It's my 2 favorite numbers. 3 and 13 came up today. You don't like what? You like even numbers? I feel like people are either one way or the other.
I like 7 and 17 and then 777.
That's like the most common one, I think, 7.
Yeah, 7. I don't know, it's just so aesthetically pleasing. Yes, it is. Don't hate on 7.
Alright, anyways, what about 320? What can I break up 320 into? Well, it's even, so it's divisible always by 2. 2 times, well, not 160, yeah. So the 4 on the outside is going to just kind of tag along until the end, where we multiply it by anything that comes out of the radical. So then this is prime, and then 160 breaks up into what? 2 and 80. And then 80 breaks up into what? 2 and 40. You have options there. And then 40 breaks up into 2 and 20, right?
Yeah.
And then 20 breaks up into 2 and 10. And then 10 breaks up into 2 and 5. Alright, so we're looking for groups of what? 2. So we have a group of 2, a group of 2, and a group of 2. We have 3 pairs, right? So anything that pairs up gets to leave as 1. We have that 4 on the outside was already there. That's going to get multiplied by whatever we take out. And then we have our first pair of 2's that leaves. We have our second pair of 2's that leaves. And we have our third pair of 2's that leaves. Now what has to stay inside the radical?
5.
The 5 that didn't get paired up. I multiply everything on the outside here, which is 32.
Yeah.
Yes. Yeah, sure. 32 radical 5. He looks so mad about it.
I don't even know how that happened.
Alright, let's do K. Ooh, really big number. Okay.
2
2
and 1,296.
and 1,900 and what?
96.
Wait, no.
1,296.
Oh, 1,296. 1,296. That's correct right there?
Yeah.
Okay. Circle the 2 because it's prime, and then what does this break up into?
2 and 648.
6 what?
48.
48. And then this breaks up into 2 and 324. And this breaks up into
2 and 160.
162.
Yeah.
And then 2 and 81, right?
Yeah.
And then what does 81 break up into?
9 and 9.
And then each 9 breaks up into
3
3
and 3.
and 3. So now we're pairing these in groups of what? 4. So we have a group of 4. And then we have a group of 4 3's as well. You guys see those down there? So the 5 has to tag along. It was already there. We have the group of 2's. We have the group of 3's. And then what has to stay behind inside the radical? 2. Now just a quick clarification tip here, or just a thing that common mistake. Don't forget, whatever your radical is, if it's a 4th root or 3rd root, don't forget to put that on there, because I have made this mistake before too. You just put the regular root and forget it. So my final answer is 30, and then the 4th root of 2. Did I say 40? I meant 30. I don't even know what I said at this point.
Yeah, you did say
My brain, my hand is faster than my speech, unfortunately. So any questions on this so far? It's easy? Okay, that's good to know. So let's try the next one. So what does 108 break up into? 2 and 54. And 54 breaks up into
2 and 27.
2 and 27. And 27 breaks up into
9 and 3.
and 9,
3 and 3.
3 and 3. We're looking for pairs of what in this case?
3.
3. We only have one pair of 3's. They're 3's. There's already 3 on the outside. We multiply it by that 3 that's already there. And then we have the 3's that got paired up. And then what has to stay behind?
2.
How many 2's?
2.
What do I do with the 2 2's that stay behind?
Multiply.
Good. So this comes out to be 9. And then the 3rd root of 4. Alright, next one. We have a negative. So, what is something we can break this up into?
2 and 125.
Yeah, that would work. Let's pick something easier off the bat, like you'll see why. Or something different. So let's pick negative 5 and 50. Negative 5 and 50. And then 50 will break up into what?
-5 and 7.
Actually both positive, right?
Oh, yeah.
So it'll be 5, and we'll actually make it, you'll see why, negative 5 and a negative 10. Because that's okay, you can have both negative to make a positive. You just gotta be able to backtrack it.
Yeah.
And then what does the 10 break up into?
-5 and 5.
Negative 5 and 2, positive 2. So, do you see why we wanted to make the 5 negative instead of the 2?
Yeah.
Because we want a pair of, how many? 3. 5, yeah, 3 of 5. So we got 3 negative 5s. That means they get to leave the radical. And what has to stay behind in the radical?
The 2.
Yeah, 2's lonely. He's staying behind in the radical. So we get negative 5. And then we have the third root of 2. There it is. Alright, last one, and then we're going to take a break. What does 1/62 break up into? 2 and 81. And if you start getting familiar with this, 81 breaks up into 4 3s, right? So you can do 9 and 9, or you can start jumping steps when you get comfortable. So this right here is a group of 4, which is what we want, right?
Yeah.
So we have a 3 that stays on the outside times the group of 3s, and then what has to stay on the inside?
The 2.
The 2. So my final answer here is 9, 4th root of 2. Okay, so a few things. We are going to take simplifying radical expressions with variables. So there are a few extra things you need to know when variables become involved. You're going to rewrite the radicand as an exponent multiples of the index. So square roots, exponents must be multiples of 2. Cube roots, exponents must be multiples of 3. Okay, cube root 3. And then what do you think 4th roots is going to be? 4. And then we're also going to learn a thing called the even, odd power rule. So this is going to sound like a riddle when you go through it. To me, this is more confusing, but then when I actually just show you the example, it'll make more sense. So the rule is, when variables are involved, if you are taking an even root of an even power and end up with an odd power answer, you need an absolute value around the odd power answer. So you'll see when this comes up, I'll show you how to check for it and to know to look for it as we go through the lesson, okay? So let's go ahead and move into the next part. So I'm going to zoom in to do these so you guys can see better. Alright, so the first one we're going to do is the square root of 16 x to the 8th. So first we're going to take the square root of 16, which is 4. And then we're going to take the square root of x to the 8th. So you can think of the variables just like we think of the factors. So technically speaking, you basically just have 8 x's multiplied together. Okay? 1, 2, 3, 4, 5, 6, 7, 8. And we're grouping them into pairs of 2 because it is a square root. So we group them into pairs of 2. And how many pairs of 2's do we have? 4. So it's going to be 4x to the 4th power. And that is how you get your answer.
Can't you just divide it by 2?
You can, yeah. The reason I wanted to show you this way is because sometimes it's not going to evenly go into it. So I just wanted to get you to understand the concept behind it. But yeah, you can. So the next one we're going to look at is something that comes up a lot when we do math in the class. So you take the square root of something to the 2nd power. What happens to the power? They go away. Now this is something that we have to pay attention to with the absolute value rule. So this is a regular square root, which means that our index is 2. We have an even power with an even index, and we end up with x plus 2 regular, which is to what power, technically? 1. Is that an odd power? Yes, so we have to put absolute value around it. So if it's an even power, even index, and you get an odd power answer, you have to put an absolute value around it. And when you see more, it'll make a little more sense. But You just put an absolute value over it when that happens. And then the next one we're going to talk about is fourth root. So we're looking for groups of 4, right? So how many ways can you group up 8 x's into groups of 4? 2. And how many ways can you group up 12 y's in groups of 4? 3. So this is where we have to be careful. This is an even power answer, that's okay. But we have an odd power answer here. An odd power answer where we had an even power with an even index, so we have to put an absolute value around that. If you get an odd answer from an even power and an even index, you have to put an absolute value around it. Next one we're looking at is number 4. How many ways can you group a to the 6th into groups of 3? 2. And how many ways can you group 9 b's into groups of 3? 3. Now, do we have to put an absolute value around b to the 3rd? No, why not? Good. The power here is odd and the index is odd. They both have to be positive to have to do that. Next one is 486. So I'm going to kind of give you guys some, like, speed this up a little, because we did the ones with the numbers earlier, so I'm going to show you like some tricks to go a little faster with these. So I know that 486 breaks up into 81 and 6. Now 6 is prime, but 81 we know 81 has a 4th root, right? And what is the 4th root of 81? Not 2, but 3. Oh, my bad. You're right. 6 is not prime. You're right. It isn't prime. Bless you. But we're not going to use it because it doesn't get us anywhere. So yeah, it's not prime. You're correct. So the 81, okay, is the 4th root, right? So basically, I take the 4th root of this one and the 4th root of this one, and I can't do anything with this. There's not 4 groups of anything, but this groups up into 4, so this becomes 3 with the 6 left behind. Okay. Now, this one was tripping people up. How many ways can you group 9 x's into groups of 4? So let's write them out. 1, 2, 3, 4, 5, 6, 7, 8, 9. I hope I have 9 correctly. So you're grouping them up in groups of 4. So I have a group of, why am I doing groups of 4 and not 2?
No, I said it's 2.
You're right, it is 2. But the problem is we have how many left over? 1. So 1 has to stay inside the radical. So we have 2 groups, and then the other x has to stay inside the radical. And what about the y's? How many ways can we group 12 y's into groups of 4? 3. So we're left with 3x squared y to the 3rd, and then the 4th root of 6x. Now, do we need to put an absolute value around the y to the 3rd? Yes, because we have an even power to an even index.
Go back to number 4 real quick.
Sure. So, we get to the stage where you can do a whole factor tree if that's what you feel confident and comfortable doing, but there's some of these that are pretty, like, you can kind of get them right off the bat. This is not one of them really, though, I guess, now that I see it. So, I know that 81 breaks up into negative 27 and positive 3. So, are either of these numbers perfect cubes, perfect cube roots? 27 is, right? And what is the cube root of negative 27? Negative 3. So negative 3 gets to leave the radical, and the other 3 has to stay behind. Now, can I take the 3rd root of p to the 2nd?
No.
No, it's got to stay. Can I take the third root of q to the 12th? Yeah, and what does it become? Q4. Now remember, what's left behind is the 3 that didn't get grouped up and the p to the second that we couldn't take the third root of. Make sense so far? Yeah, go ahead. Okay. So the next one we're looking at is number 7. So is 64 a perfect cube?
Yes.
Of what number? Not 4. So what is the third root of negative 64? Negative 4, right? Because you got to have that negative there because it's a negative. And then what is the third root of x to the 10th? Good. It's x to the third because groups of 9 groups, or 9 x's can be used up to group into 3. And then how many x's stay inside? Just 1. So does everybody understand how we got x to the third and then the x inside? So this is 9 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9. Groups of 3. 1, 2. Yeah, that's why. There we go. 3 groups of 3 and then 1 x left behind. That's how we get that. And then what is y to the 21st broken up 3 ways? 7. All that was left behind in the third root was the x that couldn't get grouped up. So this is our final answer. Number 8. So for number 8, what is the fourth root of w to the 4th? Good. And what is the fourth root of v to the 17th? V to the 4th, and then what has to stay behind? 1v. And does the w have to go in absolute value? Yes. Yeah, because it's in even, odd. And then the last one, this one's not too bad. How many ways can we group 8 into 4? 2. So it's just this. And that's all you can do with that.